Welcome to this concept explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com.
Today, let us understand a very crucial topic from Unit 1, electric charges and fields.
Yes, the behavior of an electric dipole in a uniform external field. Our mission is to make this concept simple and completely safe for your examinations.
So where should we start?
Let us begin with an everyday question. Think about a microwave oven. Have you ever wondered why it heats water so efficiently?
I mean, I know it uses microwaves, but the physics of it.
Exactly. A water molecule, H2O, is electrically neutral overall. It has no net charge.
Right. So if it's neutral, why does it interact so strongly with the electric fields inside the oven? The field shouldn't be able to push or pull it.
That's the perfect question. It seems like a contradiction, doesn't it? If the total charge is zero, there should be no force. So what is generating the heat?
There must be some internal movement or friction.
Precisely. And that's because the water molecule is a permanent electric dipole.
A dipole, even though it's neutral.
Yes. Because of its shape, the way the atoms are arranged, the electron sharing is unequal. The oxygen atom pulls the electrons a bit closer.
Ah, so it creates a negative end near the oxygen and positive ends near the hydrogen atoms.
You've got it. So even with a net charge of zero, you have a separation of charge. And this tiny arrangement, this dipole, is fundamental to so much technology.
It's like LCD screens and the microwave.
Exactly. They all depend on getting billions of these tiny dipoles to align when you apply an external electric field. But here's the counterintuitive part we must master for the exam.
Okay.
You take this neutral dipole and place it in a perfectly uniform electric field. You might expect some sort of pull.
Right.
But the surprising truth is, there is no net pull at all. None. The system only experiences a twist, a pure rotation.
Yeah. No push, just a twist. Why?
Let us unpack that. It's the core idea. An electric dipole is a positive charge, plus Q, and a negative charge, minus Q, separated by a small distance.
Okay.
We place this system in a uniform field, E. Now, what does uniform mean?
That the field has the same strength and direction everywhere.
Perfect. So the force on the positive charge, which is F equals QE, points in the direction of the field.
And the force on the negative charge would be minus QE, pointing in the exact opposite direction.
Exactly. Since the charge Q has the same magnitude, and the field E is the same at both locations, the two forces are perfectly equal and opposite.
So they cancel each other out. The net force is zero.
The net force is zero, which means the dipole does not move left or right, up or down. No translational motion.
But you said it rotates. How can something move if the net force is zero? Doesn't that contradict Newton's laws?
An excellent question. It gets to the heart of this topic. F net equals ma applies to the center of mass. Since the net force is zero, the center of mass doesn't accelerate. It stays put.
But the forces aren't acting on the center of mass.
No, they are acting on the two ends of the dipole. They are separated by a distance. And when you have two equal, opposite, and parallel forces separated by a distance, they form what we call a couple.
A couple.
And a couple doesn't produce a push. It produces a twist, a torque.
I see. So the zero net force explains why it doesn't move, and the couple explains why it rotates.
You have understood the core concept. The best analogy for this is a magnetic compass.
Okay.
When you put a compass in the Earth's magnetic field, which is more or less uniform, does the compass needle fly away to the North Pole?
No, of course not. It just rotates. It turns to point north.
It just turns. Exactly. It aligns itself. The electric dipole in a uniform electric field behaves in the very same way. It rotates, seeking alignment.
That's a very clear analogy.
To make a strong mental image, picture the dipole as a dumbbell. A red ball for the positive charge, a blue ball for the negative.
Red and blue dumbbell, got it.
Now imagine placing it in a perfectly uniform wind, which is our electric field E. The wind pushes the red ball forward and the blue ball backward with exactly the same strength.
So the dumbbell wouldn't fly away, it would just spin in place.
It would spin, yes, stays in the same location, but rotates until it's perfectly aligned with the wind. That spinning motion is the torque. And this is vital because it's the basic mechanism of polarization in materials.
So now we have the concept. What about the formulas for the exam?
Good. Let us transition to the formal language. We need the official insert definitions. Could you please read the definition for the electric dipole moment, P?
Yes. It says, an electric dipole is a pair of equal and opposite charges Q and Q separated by some distance 2a. Its dipole moment vector P has magnitude 2 and is in the direction of the dipole axis from negative to Q.
Thank you. That direction from
Useful.
negative to positive is extremely important. Never forget that.
Okay, from negative to positive.
Now let's look at the torque mathematically. We said the forces form a couple. The magnitude of the torque is the magnitude of one force, which is QE.
Multiplied by the perpendicular distance between the forces, the lever arm.
Yes, the lever arm. And if the dipole makes an angle theta with the field E, that perpendicular distance is 2a sin theta.
Ah, so torque is QE times 2a sin theta.
Correct. And what is 2 times Q times A?
That's P, the magnitude of the dipole moment.
Exactly. So we substitute that in, and we get the formula for the magnitude of the torque. Tau equals PE sine theta. This is what you will use for most numericals.
Tau equals PE sine theta. Okay.
In vector form, which is more powerful conceptually, we write it as a cross product. The torque vector tau is equal to the dipole moment vector P crossed with the electric field vector E.
A cross product. Why?
Because torque is a vector that has a direction perpendicular to both the dipole and the field. If you use the right-hand rule and curl your fingers from P towards E, your thumb will point in the direction of the torque. It shows the axis of rotation.
So the torque is maximum when sine theta is maximum at 90 degrees.
Correct. When the dipole is perpendicular to the field, it experiences the maximum twist, and the torque is 0
When sine theta is 0. So at 0 degrees and 180 degrees. When it's aligned or anti-aligned.
Perfect. Hope everything is clear so far. This deep dive is brought to you by ProfSam.com. That is ProfSam.com.
Now what about potential energy? You mentioned that as well.
Yes, potential energy, U. This is the energy stored in the dipole because of its orientation in the field. The formula is defined using the dot product, and very importantly, with a negative sign. U equals minus P dot EE.
Minus P dot E. Why the negative sign? Usually, work done by a field is positive.
This is the most critical point for understanding stability. We define potential energy such that any system will naturally try to move to a state of minimum potential energy.
The most stable state.
Yes. Think of a ball in a valley. It's most stable at the very bottom, where its potential energy is lowest. For our dipole, what is the most stable orientation?
When it's perfectly aligned with the field, angle theta is 0.
Correct. So we need our formula for U to be at its most negative, its minimum value, when theta is 0. Since the dot product, P dot dot E, is PE cos theta, and cos of 0 is positive 1.
We need that negative sign in front to make the energy U equal to minus PE, its minimum value.
You have understood it perfectly. The negative sign ensures that the most stable state alignment corresponds to the lowest possible energy.
That makes sense.
Let us solve a very simple problem. Imagine a dipole with moment P equal to 1 × 10 to the power minus 30 coulomb meter. It's in a field E of 1,000 newtons per coulomb at an angle of 60 degrees. First, what is the torque?
Okay, torque is key E sine 60. So that's 1 times 10 to the minus 30 times 1,000 times. Sine of 60 is root 3 by 2, or about 0.866. So that's 0.866 times 10 to the minus 27. Oh, wait, 1,000 is 10 to the 3, so it's 8.66 into 10 to the minus 28 newton meters. A very tiny torque.
Excellent calculation. And its potential energy at that 60-degree angle.
That would be U equals minus PE cos 60. Cos of 60 is half 0.5, so it's minus 1 times 10 to the minus 30 times 1,000 times which gives.
U equals minus 5 into 10 to the minus 28 joules. The negative value means it is in a relatively stable state. Perfect. And understanding this energy is the bridge to our next unit on dielectrics and polarization. Now, please listen very carefully. Let's talk about the silent killers. These are the common misconceptions that can cost you easy marks.
Okay, perfect.
Misconception number 1. Students often write that a dipole always experiences a net force in an electric field.
But we just proved that's not true.
But they forget the condition, so the correct statement is...
In a uniform field, the net force is 0. There's only torque.
And when is there a net force?
Only in a non-uniform field.
Yeah.
Because the field strength E would be different at the positive and negative charges.
Precisely. If the field is stronger on one side, that force will be bigger, and there will be a net pull towards the region of the stronger field. You must remember this distinction.
Uniform field, rotation only. Non-uniform field, rotation and translation.
Correct. Misconception 2. Students think the dipole just snaps into alignment instantly.
But the torque causes an acceleration, not an instant movement.
An angular acceleration. Correct. The alignment is a gradual, time-dependent process. It might even oscillate a bit before it settles.
I see.
And the third one, about energy. The wrong idea is that potential energy is highest when the dipole is aligned with the field.
They probably think alignment takes effort, so it must be high energy.
Exactly that thinking. But what is the correct concept?
The correct concept is based on stability. Alignment is the most stable state, so it must be the state of lowest potential energy. That's a theta equals 0, where U is minus PE.
And the highest, most unstable energy state is when?
When it's anti-aligned. At 180 degrees, where cos is minus 1 and U becomes plus PE.
Excellent. You have avoided all three traps. Now, to lock this in for the exam, let's use a few memory anchors. First, a simple mnemonic, UTA.
UTA.
Uniform field leads to torque only, no net force, which causes alignment as the final state, UTA.
Uniform torque alignment. That's easy to remember.
And a catchy phrase to hold the idea, uniform field. No push, just twist. The dipole rotates until at rest.
No push, just twist.
Finally, a physical gesture. Hold your two hands apart, like a dumbbell. That's your dipole. Imagine the field is pointing away from you. It pushes your positive hand forward and pulls your negative hand backward.
Okay.
Now what happens? Your body doesn't move, but your hands rotate until they are aligned with the field direction. That pure twisting motion, that is the torque in action.
Right. I can feel the rotation. That helps.
Good. Let us conclude this deep dive with the three most critical exam-safe summary points. Number 1.
In a uniform electric field, an electric dipole experiences zero net force.
Number 2.
The dipole experiences a torque given by tau equals P cross E that tries to rotate it into alignment with the field.
And finally, number 3.
The potential energy, U equals minus PE cos theta, is minimum and therefore most stable when the dipole is aligned parallel to the field at theta equals 0.
Excellent. You have mastered the concept. To get maximum marks in 12th CBSE physics, chemistry, and maths, visit ProfSam.com.
That is PROFSam, right?
Yes, PROFSAM.com. Wishing you the very best in your studies.